In triangle ABC, angle BAC is alpha, angle ABC is beta, and angle BCA is gamma. We can see all that on the diagram. The point O is situated inside triangle ABC such that angle OAB is equal to angle OBC is equal to angle OCA is equal to theta. These are also shown in the diagram. So this information is shown in the diagram below. Using the sine rule, show that sine theta is equal to OB divided by OA sine beta minus theta. So if we just look at that particular triangle, so let's just draw it here like so. The angle just here, which is this angle, would be beta minus theta. This is O, this is B, this is A. And so by the sine rule, OA divided by sine of beta minus theta would be equal to OB divided by sine theta, because this one up here is theta. We can see that on the diagram just there. Rearranging that gives us sine theta is equal to OB divided by OA sine beta minus theta. Hence, show that sine cube theta is sine alpha minus theta, sine beta minus theta, sine gamma minus theta. Well, from part A, sine theta is equal to OB divided by OA sine beta minus theta. Can we get something similar from the triangle at the bottom here, and then from the other triangle AOC? Well, I'm sure we can. This angle here, for example, would be gamma minus theta. The angle at the top here would be alpha minus theta. And so we could use those triangles in a similar way to what we did here to get the following results. So from triangle OBC, we would get sine theta is OC over OB sine gamma minus theta. And from triangle OAC, we would get that sine theta is equal to OA over OC sine alpha minus theta. So if we do sine cubed theta by doing that one times that one times that one, we're going to do that one times that one times that one. And so that's going to be OB over OA sine beta minus theta times OC over OB sine gamma minus theta times OA over OC sine alpha minus theta. And you can see this OA is going to cancel with that one, the OB is going to cancel there, and the OCs are going to cancel. And so we would get sine alpha minus theta, sine beta minus theta, and sine gamma minus theta. We're now asked to prove the identity cot P minus cot Q is equal to sine Q minus P over sine P sine Q. I'm going to do this by going from the right to the left. So sine of Q minus P over sine P sine Q would be equal to sine Q cos P. Take away cos Q sine P over sine P sine Q, which is sine Q cos P over sine P sine Q. Take away cos Q sine P over sine P sine Q. So we've got some cancelling happens here. And I just cancelled incorrectly there. It was obviously these ones that went. And so cos P over sine P is cot P. And cos Q over sine Q is cot Q. So we've proven the identity. Now in part 2, hence show that cot theta minus cot alpha, cot theta minus cot beta, cot theta minus cot gamma is cosec alpha, cosec beta, cosec gamma. So let's think about this. If we've got cot theta minus cot alpha, and then we've got, this is part 2 of this, this one is cot theta minus cot beta, and then we've got cot theta minus cot gamma. Using the identity we just proved in part 1, this first one is going to be sine of alpha minus theta over sine alpha sine theta. Then we'll have sine beta minus theta over sine beta sine theta. And then we'll have sine gamma minus theta over sine gamma sine theta. Now, if we go back to identities all the way back at the beginning of the question, we can replace these signs. We can say OC over OA sine theta times OA over OB sine theta times OB over OC sine theta all over sine alpha sine beta sine gamma over sine cube theta. And we know there's all sorts of cancelling goes on here. So all of those go. So what we have is sine cube theta over sine alpha sine beta sine gamma sine cubed theta. And those will cancel. And so we have 1 over sine alpha sine beta sine gamma, which is cosec alpha, cosec beta, and cosec gamma as required. So finally, we want to find the value of theta for which triangle ABC is a right-angled isosceles triangle. Well, let's imagine that it is right-angled at B. Or rather, let's say, let's go back and look at the original triangle. So let's say that beta is 90 degrees. That would then make alpha and gamma 45 degrees. So that's what we're going to do. So we're going to make this one a right angle. Those two, if it's isosceles, will then be 45. So I'm going to let beta be equal to 90 degrees and alpha be equal to gamma be equal to 45 degrees. So we then have cot theta minus cot 45 degrees. Cot theta take cot 90 degrees. Cot theta take cot 45. Now, cot 45 is 1, so that's 1. And cot 90 is 0, because tan 90, remember, is undefined. So that becomes cot theta take away 1 squared, and that needs to be equal to 2. And that comes from the other side of the identity here, which is that this will be 1 over sine 90 sine squared 45. And that's just from the identity that we proved up here. And so, with sine 45 being root 2 over 2, squaring that, sine 90 being 1, that becomes 1 divided by a half, giving us the 2. So expanding out, we get cot cubed theta, take away 2 cot squared theta, plus cot theta, take away 2 is equal to 0. So onto the calculator, and I think what we want here is to go into the equation solver. F2 is a polynomial. We have a cubic, and our a value is 1. Then we have negative 2. Then we have 1 and negative 2. And then we want to solve. And we get the value 2. So cot theta is equal to 2, which means that tan theta is equal to a half. And we can just find that on the calculator. It's 26.6 degrees, or 0.464 radians.